Alright, today's lesson is about energy. So what we know is when we do work, what ends up there is we get tired. And the reason we get tired is because we use energy. Right, then we've got to rest, eat, whatever, to replace that energy. So from what we kind of understand in our everyday life, if we're using that energy, then we're doing work. But there's the thing about energy is in that there's conservation of energy, as it's called. And so what we say is that energy doesn't actually disappear. So energy, one of two things happens. You transfer it to something, or it's transformed. So the transferring is, you might grab a ball and throw the ball, so the energy that you've used in your muscles, etc., to throw that ball has then been transferred to the ball and the ball moves. So it's got some movement energy, kinetic energy. Transformed, when you throw that ball and say, for example, you throw it into a wall or something, and then it would stop. But what you would actually is you would hear some sound, and there'd be a little bit of heat, not that you'd be able to probably measure it. So that's been transformed. So conservation of energy says that energy is neither created or destroyed. Alright, and so that's conservation of energy. So in terms of adding the work, so the work done, say, by something is transfer of energy from and the opposite also applies. Work done on is a transfer, again, a transfer of energy, but this time to. So if something's done, work's done by, there's a transfer of energy from. If work's done on, there's a transfer of energy to. So as I mentioned, first of all, we can work equals a change in energy. So work and energy are linked. So if work and energy are linked, then they have the same unit. So unit is can't spell joule. Let's go back here. Joule, joule, J. All right, work and energy linked. Okay, so transfer of energy from and energy to, work is change in energy. So what are these energies? So the first one is that we'll look at, and we've actually used these first couple before. Well, I can't spell energy. Let's go back here. E-G-Y, that's better. Did them in Unit 2, and so just recalling. So kinetic energy is energy of movement. So something moves, something has kinetic energy. And so kinetic energy, EK, E for energy, K for kinetic, as you hopefully remember from Unit 3, half mv squared. Now, because work equals change in energy, and if we do work on something, it's going to be, in this case, the change in the kinetic energy, or keep consistent with the symbols that are used up here. This is the change in kinetic energy in this case. So, of course, that is our final minus our initial. And if we're using the symbols V and U as the speeds, then change in kinetic energy can be written as half mv squared minus half mu squared. Alright, so let's look at an example. Okay, so here's our example. Body of mass 4 kilograms, moves with the speed of 3 metres per second, accelerates to a speed of 6 metres per second. So what is the change in kinetic energy and the work done? Okay, so do part A first. The change in the kinetic energy is our final, I should say, minus our initial. And so our final speed, V, that's it, the 6, and our initial U is the 3. So it's a half times 4 times 6 squared minus a half times 4 times 3 squared. Get our calculators out and figure that out. 5 times 4 times 6 squared. So that's 72. And a half times 4 times 3 squared is 18. So 72 minus the 18, and we have 54 joule of kinetic energy change. Alright, in part B, asks about the work done, and the relationship between work and energy is that work is the change in energy. And in this case, we've got a change in kinetic energy of 54. So the work done, 54 joule. Alright. So next is, again we've used this in some questions. Gravitational potential energy. Alright, so gravitational potential energy, if here's the Earth, and we've got something above the Earth, and we say it's got gravitational potential energy. Holding it there, it just stays there, but if we let that go, that would fall down to the ground. So we say then that at this point up here, it's got some gravitational potential energy. And so what does that gravitational potential energy rely upon? Well, we're using the symbols UG, U for potential energy, rather than over here we used for kinetic, we used E. So U is potential, and G is gravitational potential energy, because it's potential because at the moment it's not actually doing anything, any work as such. It's just sitting there, but let that ball go, and as I said, it falls down, so then it starts to move. So we've got kinetic energy. So change from gravitational potential to kinetic. All right, so what does it rely on? Well, it relies on the mass. It relies on gravity, and it relies upon the height, mgh, and that's in joule. Now, this is great for stuff that's close to Earth. Now, when it's not close to Earth, and we'll get more onto this when we get to the field stuff, the gravitational field in particular, is that this G here, it actually depends on the distance from the planet, or whatever. I'll just say planet. All right, and so when we're close to Earth, that distance doesn't change much, so G doesn't vary much. So close to Earth, this mgh is good, but for large distances, it's no good. And for large distances, we've actually got to use a different method. Right, and the method we've got to use, we've got to rely on this here, which is a graph. And what this graph is gravitational force and distance from, in this case, centre of the Earth. All right, so as you can see, that's a curve, not a straight line. So, but if we take one little square, for example, so I take this little square here, or rectangle, this side here, what is that? That's length, of course, but that's a force. All right, this, and this other side length, this one here, the width, what's that? Well, that's a distance. So if I want to work out that area, I would do force times distance, and Fx is work equals Fx. And what else is work? Work is change in energy. So from that, we say that what we can use then is the area under gravitational force versus distance graph is the change in the gravitational potential energy. All right, so for these, we need to use a graph. Now, the thing that you need to keep in mind about this is that this 0 point down here, use red, so this 0 point here, in terms of the distance, that is from the centre, and it actually says that over here. Let me erase those things so we can. Alright, so it actually says here from the centre. So these graphs are from the centre, and on this particular one, what we've got is we've got this dotted red line here. And so, as it says there, that's the radius of the Earth. So that's on the Earth's surface here, which relates to a gravitational force of 98 newtons. So 9.8 is G, gravitational. All right, so we've got a question, so let's have a look at our question. Okay, our question says, using the graph in figure 7.42, that's the one on the previous page, but I'll just put another copy of that here. Right, so there's another copy of it. Calculate the work done against the gravitational force in moving a 10 kilo object from a radius of 1 by 10 to the 7 orbital radius to 2 by 10 to the 7. Now when we look on the graph, here's our 1 by 10 to the 7, here's our 2 by 10 to the 7. So we're talking about the work done against the gravitational force between those 2 points. Alright, so we've got our object, if we put our object around our Earth, and so we've got our object here, and we move it out to there, how much work has been done. So, as we previously said, and as it shows here, the area equals the energy change. So what we need to do is we need to find out that area. Now, because it's a curve, it's a little bit more complicated. Now, mathematically, if we knew the equation of the curve, we could use some calculus to do that. But in physics, we're not expected to do that. So what do? The way we do it, we approximate the area. And we approximate the area as best we can by counting squares. Might seem inaccurate, but that's what we do in physics here, and that's well accepted. So then have a look at squares. Any full squares, so 1, 2, 3, 4, 5, 6. There's 6 full squares. Oh, missed one down here, 7 full squares. So we count them. Now, then what the convention is, anything that's more than half a square you count as 1, and anything that's less you don't. So that one's definitely more than half. And then this bit up here, I'm going to count that as more than half as well. So 1, 2, 3, 4, 5, 6, 7, 8. So in this case, we've got 9 squares. All right, so the area of 1 square, or rectangle, call them squares. So I need to know that there, and that there, by looking at that scale, should be 10. And this here, and when we count that, if that's there 1, then this one here is going to be 0.25. Now, don't forget to look here, and this is an error that people make. So they forget to have a look at that and see what our units are. So the gravitational one is just straight 10. There's nothing special there. But this other one here on the horizontal axis, it's 0.25, but 0.25 by 10 to the 7. So when we do that, we actually end up with 2.5 by 10 to the 7 for the area. Now, that's the area of 1 square. We've got 9 squares. So what we know is the work equals the change in the energy, which is equal to the area, which is equal to 9 times 2.5 by 10 to the 7. And so when we get our calculator out and do that, 9 times 2.5, 10 to the 7, we get 2.25 by 10 to the 8 joule of work. So let's just check to make sure I've answered the question, what the question wants. The question wants, in the end it says, hence find the gravitational potential energy gained. So the work done is the change in energy, and then so our change in our gravitational is 2.25 10 to the 8 joule. Okay, so now we've got some text questions. So work on those text questions. Don't forget my notes are on the website. And anything that was not clear in that you need to get clarification on, make sure you ask me.